Good morning, ladies and gentlemen. Today is the second part of our electrostatics lesson, which is about Coulomb's law. So, who was Charles de Coulomb? What did he discover? Well, basically, first here's a nice picture of Charles de Coulomb from Wikipedia. He was a French scientist who lived in the 1700s, and he had created a device called a torsion balance, which is basically a device that measures very weak forces. And here's another diagram, actually, that's pretty good. This one's used for gravitational forces, but it's the same idea. And he was able to discover the exact relationship between the charges themselves and the relationship between the distance between the charges and the force exerted. So, for his work, the unit for charge is named after him. So Q is named after him. But ultimately, he discovered the force relationships between charges and distance. Okay? Quick recap from before. What is the charge of 1 electron, 1 proton? Is exactly the same, which is 1.6 times 10 to the negative 19 coulombs. I'm just going to write that down now because we're going to use that again and again in this unit. So Coulomb's law, let me just move this up a little bit. Looks like this. The electrostatic force, Fe, is equal to 1 over 4 pi epsilon naught, so 4 times pi times the vacuum permittivity constant, times the first charge, times the second charge, divided by the distance between the two objects squared. So R is the distance between the charges. Q is the charges themselves, measured, of course, in coulombs. Now, the thing is, don't worry too much about the vacuum permittivity constant. This is 1 over 4 pi epsilon naught. The fact is, we scientists have just written a shorthand way of writing out 1 over 4 pi epsilon naught as K. K is basically equal to 1 over 4 pi epsilon naught, and it's called the electrostatic constant. It has a value of 9 times 10 to the 9th Newton meters squared over Coulomb squared. It's extremely important to note, okay, that in terms of the positive and negative signs, we never include the charge signs within the formula itself. The only thing that charge signs are going to be used for are to determine the direction of the force based on whether it is attracting or repelling. And we'll do some examples with that. Now, I would like to point out, however, that Coulomb's law is very similar to another law. Fe is equal to K Q1 Q2 over R squared. Has a lot of similarities with Fg equals to G M1 M2 over R squared. Gravitational force and electrostatic force are both two of the fundamental forces within the universe. And R means distance for both of them. The only difference is that we deal with masses instead of charges with gravity. But it is also important to note the difference between the values of the constants themselves. K is equal to 9 times 10 to the 9th Newton meters squared over Coulomb squared. versus the universal gravitational constant is equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. Look at the value of the exponent. Electrostatic force is an incredibly great force. It's so strong that it binds the atoms together. Okay? Gravitational force is very weak, but the only reason we feel the gravitational force is because the Earth itself has such a tremendous mass, 10 to the 24th kilograms. But we can feel the same strength of forces with very minute charges. Okay, so here's our first example problem. Determine the magnitude of the electric force on the electron of a hydrogen atom exerted by the single proton in the nucleus. Assuming, of course, that it is a single ball that rotates around another ball. So we'll take a look at what that looks like. Over here, we can see that we have basically the electron and the proton at a distance of 0.53 times 10 to the negative 10 meters on average. Okay, in reality, it's impossible to measure this value. So in this case over here, if we want to solve for the force between the two charges, Fe would equal to K Q1 Q2 over R squared is equal to 9 times 10 to the 9th Newton meter squared over Coulomb squared. The first charge is a proton, which is, of course, 1.6 times 10 to the negative 19 Coulomb, times the electron, which is also 1.6 times 10 to the negative 19 Coulomb. 0.53 times 10 to the negative 10 meters squared. So the value of 8.2 times 10 to the negative 8 newtons, which may seem like a tiny number to you, but remember, these are incredibly small charges. In fact, if we were to calculate the gravitational force between the electron and the proton, we get a very different answer. In fact, let's calculate that out. So right now, there's an electrostatic force of 8.2 times 10 to the negative 8 newtons, about. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. So if I were to solve for the gravitational force, G times mass 1 times mass 2 divided by the distance (3.6) times 10 to the negative 47 newtons. Not even close. Okay, so you can see that electrostatic force is a tremendously powerful force as compared to gravitational force. Now, also be aware that some of the more common types of problems with Coulomb's law involve multipliers. And in this case, they ask, we'll just do a couple of examples. If you double the distance between the two charges, what happens to the electrostatic force? Well, Fe is equal to K Q1 Q2 over R squared. And if you just assume that everything was equal to 1, if you double the distance, we can see that we pull out an answer of 1 over 2 squared, which is 1/4 the original value. Do not forget the square sign. That's a very common mistake. Or if I half the distance, I would get 1 times 1 times 1 over 1 squared, but now it would become 1/2 squared. And 1 over 1/4 is the same thing as 4 times greater. More complicated questions would involve multiple charges. And just keep in mind that Coulomb's law only deals with two charges at a time. So when we have multiple charges, we just have to deal with any pair of charges at one time. So right now we have charges A, B, and C. They say A is a positive charge, B is a negative charge, and C is a positive charge. They ask, what's the net force on sphere B? And this is when the charge signs matter, because we have to figure out what's going to happen between the two forces. So right now, between spheres A and B, I know that they are opposite charges, so they are going to attract towards each other. So therefore, sphere A would feel a force one way, and sphere B, of course, would feel the exact opposite force in the opposite direction, because they are going to attract towards each other. Meanwhile, B and C are both opposite charges as well, so they're going to attract. So we have FBC and FBC. Okay? And yes, sphere A and sphere C will interact with each other as well. In this case, they're both positive charges, so they would repel. So in this case, if I really needed it, it would be FAC going to the left and FAC going to the right. It's the same exact force on both sides. Now this question only asks for the net force on sphere B. So I have to solve for FAB and FBC. So FAB will equal to K Q1 5 times 10 to the negative 5th Coulomb. Notice I did not include charge sign in here. Times Q2 7.6 times 10 to the negative 6th Coulomb divided by the distance between the two charges, 25 centimeters or 0.25 meters. In this case over here, the total is 54.72 newtons left. Meanwhile, force BC would equal to 9 times 10 to the 9th. Sphere B was 7.6 times 10 to the negative 6 coulombs. Sphere C was 1.3 times 10 to the negative 5th coulombs, divided by a distance of 0.15 meters squared. 39.52 newtons right. So in this case, when we're looking for the net force, we will combine the 54.72 with the 39.52. And since they're in opposite directions, you would subtract, and you get an answer of 15.2 newtons left. If we had wanted to solve for the force between spheres A and C, in that case, we would have just used the total combined distance of 40 centimeters. For our next question, we have 3 charges placed in a vertical column, and sphere A, and they're all positive, and they're asking for what's the net force on sphere C. So if we're actually to take a quick look at this example over here, I have 3 positive charges, the first charge, second charge, and the third charge. And the first 2 charges are being held in place while the third charge is being let go. So because they are all positive, they are all going to repel each other. You can see, in fact, that positive charge gets repelled away. And we're going to calculate what's that initial force. In other words, for that red line, how much force is being created. Okay? And that's going to be the total force of AC plus BC. So right now, FAC, as well as FBC and FBC. So since these 2 forces are pointing in the same direction, we are going to add the two forces together. So FAC is equal to 9 times 10 to the 9th times charge A, 3.5 times 10 to the negative 2, times charge C, 5 times 10 to the negative 5 coulombs, divided by, now it's going to be the total distance. In this case, the total distance will be 75 centimeters, so it will be 0.75 meters squared. 28,000 newtons downwards. For force between spheres B and C, be 9 times 10 to the 9th times 2 times 10 to the negative 3rd times 5 times 10 to the negative 5th divided by distance between the two of 0.35 meters squared. And we get an answer of 7,346.9 newtons down. So when you add the two of them together, you get a total force of 35,346 newtons downward. Now, I want you guys to note, however, that force is only lasting for the initial second when it's first let go. Because if you take a look here, red represents force, blue represents the velocity. You can see that the force gets smaller and smaller and smaller. Now, why does that happen? It's simply because the charge is moving further and further away. So even though the velocity is increasing, the acceleration is decreasing. It's not negative yet, but it's not accelerating at the same rate as it initially was because it's further and further away. Okay. In this question over here, while the previous problems dealt with charges in a line, this problem is more difficult because you're dealing with two dimensions of motion. We have three positive charges that are placed equidistantly away from each other, but at the same time, because they are on the x and y axis, the forces are going to look a little bit different. Between charges A and B, force AB is going to point downward, while force BC is going to point to the right, which means that overall we're going to have to use Pythagorean theorem to solve for the total force on charge B. So, using the formula Fe equals to K Q1 Q2 over R squared, we have 9 times 10 to the 9th Newton meter squared over Coulomb squared times 5.5 times 10 to the negative 4th Coulomb. And since there's two of them, I'll just square that, divided by 0.5 meters squared. I get a total force of 10,890 newtons. As FBC and FAB are exactly the same as each other, now if I do Pythagorean theorem, that means I'll do 10,890 squared plus 10,890 squared and square root that. And you end up with a total force of 15,400.78 newtons. If we wanted to solve for the angle as well, in this case, because they are equal to each other, the angle is 45 degrees, but we would use inverse tan y over x, so that would just be 10,890 over 10,890. In this case, will equal to 45 degrees. It becomes more complicated when you're dealing with charges that don't use Pythagorean theorem as clearly. In this question over here, we're trying to look for the total force on charge 3. Now we know 2 and 3 are going to repel away from each other, so here's F23, and charge 1 and 3 are going to attract towards each other. So this problem is made more difficult because of the fact that I'm going to have to take this force and break it down to x and y components after I actually solve. But let's just actually first solve for F13 and F23. F13 is equal to 9 times 10 to the 9th times 65 microcoulombs. Now, micro means times 10 to the negative 6, so it's times 10 to the negative 6 coulombs times 86 times 10 to the negative 6 coulombs, divided by a distance. But what's the distance here? If you notice that we do have a right triangle, we can use the Pythagorean theorem to find that the total distance is 60 centimeters between those two charges, which means that this becomes 0.6 meters squared. So F13 is equal to 139.75 newtons. Meanwhile, F23 is equal to 9 times 10 to the 9th times 65 times 10 to the negative 6 coulombs times 50 times 10 to the negative 6 coulombs divided by a total distance of 0.3 meters squared. So F23 is equal to 325 newtons. Now, F23 is already pointing on the vertical axis upwards, but we have to break down F13 into x and y components. We have already the angle of 30 degrees. We are given the angle of 30 degrees down here, so we can use that to break that down into x and y components. So in this case, the x component, so F13x, will equal to 139.75 times cosine 30, which is equal to 121 newtons, while F13y is going to equal to 139.75 newtons times sine 30, which equals to 69.88 newtons. So now we have one x component. This y component points downward. This y component points upward. So overall, for our two y components, they're going to subtract from each other. 325 minus 69.875, our y component ends up equaling to 255.125 newtons. Our x component is still 121 newtons, which means that our total force using Pythagorean theorem ends up equaling to 282.36 newtons, an angle of inverse tan y over x equals to 64.63 degrees above the x-axis. So here's my final answer, which is quite complicated because of the fact that we have to use vectors, but you just have to remember how to break down vectors into their x and y components.